Hello, and welcome to Lesson 27 of this Introduction to Calculus with Wolfram U. The topic of this lesson is the substitution rule. So let's begin with a brief overview of the lesson. So in the last lesson, we talked about some rules for calculating integrals, and we learned a few simple rules. For example, we can now do the integral of x squared and get back x cubed over 3. So that's x to the power of a, giving you x to the power of a plus 1 over a plus 1, the power rule. But the rules we learned cannot help us in more difficult cases. So for example, if I give you the function 10 times sine of 3x, then those rules will not work, and they will not work for this harder problem involving a square root, a radical. So you know the functions and their plots, and what you notice is that these are quite interesting functions, so surely you would like to integrate them. The question is, how do we do that? And that is the goal of this lesson. So the goal of this lesson is to try and calculate such integrals using what is called the substitution rule. But to do that, I must recall the chain rule for you. So the chain rule says that if you have two functions f and g, so you have f of x and g of x, then the derivative of their composition, f of g of x, is f prime of g of x times g prime of x. So here's the rule a little more formally using d, and you get back the answer that you expected. Now, of course, every time you have a rule for derivatives like this one, then you have a rule for integration. So now that says that the integral of f prime of g of x times g prime of x is f of g of x. And that is the basis for the substitution rule. So let's go a little deeper and talk about the substitution rule. So let's say you want to evaluate this integral over here. What we do is, to simplify things, we set u to be g of x. So now you get f prime of u, and then you get this g prime of x dx. But then if you think about it, the derivative of u is g prime x. So that says that, roughly speaking, du is g prime x dx. That's a differential statement, but it's correct. So basically what you've done is to reduce this rather difficult-looking integral on the left to a rather simple-looking integral on the right. And that is the substitution rule for integrals. So for example, if I said find the integral of 3 times sine of 3x dx, then you set u to be 3x. So du is 3 times dx, because that's the derivative of 3x. So that 3 over here and the dx over there combine, and you get sine of u du. But then we can't stop over here because u is 3x, so the answer is negative cosine of 3x. And you can check that directly with integrate, and you do get back the right answer. So that's the rule for substitution. Namely, you set u to be g of x and then proceed from there. So as an example, let's take another trig function. So 10 times sine of 3x. So again, you set u to be 3x. So du is 3 times dx. But then you have a 10 over here. So you make a small adjustment and write it as 10 over 3 times 3. And so you get back that the integral really is 10 over 3 times sine u. You integrate that. But then recall that u is 3x. So you plug back that in, and you get back the exact answer, which is what integrate would give you if you tried it directly. Okay, so let's go a step further now and talk about an algebraic function. That's the second function from the introduction. So here you think of this inside the square root sign as being u. So u is x cubed plus 3. So du is 3x squared dx, because that's the derivative of x cubed plus 3. But then you tell yourself you've got a 2 over here, so we need a small adjustment. So we write it as 2/3 times 3. And so you have that the integral is 2/3 of square root of u with respect to u. You plug in the expression for u, and you get back the answer in terms of x. And of course, integrate gives just the same answer in this case. So let's now go on to a slightly harder example where you have a kind of a rational algebraic function. And here you set u to be 5 minus 5x squared. So du is negative 10x dx, because that's the derivative of u. And then you tell yourself that you have a 2x over here, so we need a small adjustment. So write as negative 2 over 10 times negative 10, and you get back the integral in terms of u. Over here, you plug in the expression for u as 5 minus 5x squared, and of course, integrate will give you back just the same answer in this case. Okay, so slightly harder example, you have f of x is x cubed times square root of 3 minus x squared. So you set u to be 3 minus x squared. That's what's inside the square root sign. So du is negative 2x dx. Now there's a problem. You need to rewrite the x cubed carefully as the 2x bit, the negative 2x bit from here, and the part that's left over, which is x squared, but x squared is just 3 minus u. That's how I get the part over here. So the integral becomes negative 1/2 times 3 minus u times square root of u. You integrate that. You plug in the expression. And of course, integrate will give you just the same answer in this case as well. Well, there's a slight difference because you have a negative sign inside over here and outside, but essentially they're the same answer. Now, the point is that I have two answers, one in terms of u and the other in terms of x. As far as this example goes, it's the x answer that matters, but when you go on to definite integrals, then you want to actually plug in limits, and at that point, we have two ways of going about it. So first of all, what you could do is you could work with the expression involving x, the x answer, and plug in the upper and lower limits. So let's say if you want to go from 0 to 1, you plug in the value of the x answer at 1, and then at 0, and you get back the answer over here. But you can also keep the u form. And if you do that, you've got to be careful, because when x goes from 0 to 1, then u goes from 3 to 2. That's because u is defined in terms of x. So here's the answer again from the u method, and you get back just the same result, and you can check it all with integrate, and you have the first answer is the u answer going from 3 to 2, the other one's from 0 to 1 for x, and you get back the same result in both the cases. So the point is that when you have a definite integral, then you could either work in the u picture or the x picture, and they are both convenient in some ways. The u answer tends to be simpler, but you need to change the limits. The x answer tends to be more complicated, but then you have the limits given to you, so you should decide which one is better in each case. So that brings me to the end of this lesson, and the main point is the substitution rule lets you calculate integrals using the chain rule in reverse. So this rule is essentially a reverse chain rule. So what you do is you always begin by making a substitution u, a suitable one, then you find du and modify the integral as required. Then you plug back the expression for u after integrating, and you get back the result. But of course, you're working with definite integrals. You could either work with the original endpoints and x, or change the endpoints and work with u. So that's the essence of this rule, and in the next lesson, we'll apply these ideas to compute the area between two curves. But before doing that, do review the lesson. It's quite a difficult lesson because you'll need this rule again and again, and you must have some practice with applying it. So I'll stop over here. Thank you very much.